All right, so our next example is often referred to as the drunkard's walk. And I like this example a lot just because it's kind of fun and I get to make my hands float about a whole bunch as I describe this drunkard walking around. So what's going to happen in this particular example is that we're going to have some drunkard who is going to be stumbling between two key locations. The key locations are going to be the drunkard's home and a bar. If this drunkard ends at either of those two locations, they're going to get sucked in and they're never going to leave. Basically, it's the drunkard being like, ooh, bed, I'm not leaving. I don't care if you call me, text me, do whatever. I'm stuck at home. I'm not leaving. And on the other side, we're going to have the bar, and it's going to function basically the same, is that if the drunkard ends up in the bar, they're not going to leave either. Basically, like, you can call, text me, do whatever you want. I'm staying in this bar. I'm happy here. In between those two things are then going to be some of these nice kind of little transient states. Basically, they can move between them kind of left and right until they ultimately end up at one of these absorbing points. So this particular little chain then is a little bit different than some of the ones that we saw before, and then we're going to have this existence of some of these absorption points. So it's not as interesting to see where somebody ends up because we know that they're going to end up in one of these two things. It's going to then become interesting about where we start and which one do we tend to get pulled to. Basically, if we start really close to home, are we more likely to end up at home? Or if we start really close to the bar, are we more likely to end up at the bar? And then what are those probabilities going to be? So that's how this little game is going to be set up. To give us some kind of fluidity in the middle, I've introduced three middle states, which you could think about as essentially, I don't know, let's say blocks. So let's say drunkard and bar are a few blocks apart. So you have block 1, 2, and 3. What's going to happen is that I may place the drunkard, let's say, just at some random state. We'll put them at 2. What's going to happen is that they're going to essentially either stumble forward towards the bar or they're going to stumble backwards back towards home. And I'm going to identify this kind of stumbling action with a probability. So here this probability is, let's say, 0.5. So he's going to flip a coin, walk forward, walk backwards, depending on whether or not the result is, let's say, heads or tails. So on heads, they're going to move towards the bar, and on tails, they're then going to move back towards their home. So what's going to occur then is a pretty nice little transition matrix, as well as this nice little state diagram. The thing to note here is that I have a whole bunch of zeros, which I've definitely not drawn. The way that this diagram is going to exist is that things are only linked next to each other. So 0 and 1 are linked together. I don't have an arc that's going to go from like 1 up to 0 that has a 0, just because that makes that thing really messy and junky. So I've added this extra little comment that says any arrow that I didn't draw is assumed to be a 0. So we have the home and the bar. Those get this notion of being an absorbing point because they're going to have the 1s on them. So if I end up there, I'm stuck. Everything else then is going to have even money forwards and backwards. So 50% forward, 50% backwards. So my little matrix down below, this big array, is going to have 5 rows and 5 columns, 1s in the top left and the bottom right, and then a whole bunch of 0s and 0.5s scattered throughout the entire thing. So we have diagram, we have this thing. So then the question becomes, okay, well, let's let this thing slowly evolve. So if I place the drunkard at 2 and kind of let them wander around, where are they more likely to end up? If I put them at state 1, if I put them at state 3, where are they more likely to end up? So what ends up happening is that if I raise this thing to larger and larger powers, you're going to see all those little middle terms are basically going to become zeroed out. So if I print out, I think this is like P10 or something like that, what you're going to see is that most of the stuff in the middle is going to be 0, which is meaning that this drunkard has been absorbed into one of those 2 points. If you remember, I have home as being that one and then bar as being that one. And you can then read what those probabilities of ending up in one of those locations fairly easily. So if I look at this one, it would be, well, if I started at home, what's the probability that I end up at home? The answer there is 100%. The next one down then would be like, okay, if I started 1 click away from home, what is the probability that I end up at home? Here, that answer is actually 0.75. And it's kind of worth looking into. Basically, you start here. There's a 50% chance that you go home right off the bat on the first move. There's also a 50% chance that you move forward. Well, once you move forward, you can then stumble backwards and then stumble back home. And that's where you can kind of start to see this dancing taking shape. I like this kind of fluidness. There's a whole bunch of different ways that the drunkard can end up at home. They could walk forward, like, oh, they're really close to the bar, and then they stumble back home afterwards. So there's a lot of dancing one can do between those two locations. But if you start one click away from home, this is going to kind of stabilize into about 75% of the time you're going to end up at home. On the flip side, there's a 25% chance that you're going to then end up in the bar. Basically, enough things have to occur for you to pull into that bar. You have to kind of flip heads over the number of tails. And you have to kind of get what? Three-way head start to go 1, 2, 3 into the bar. But you could also go do, 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 do. So you have to kind of get this extra little bit. Hopefully some of the Turing machine discussions coming into play as well. It's like, how do these ledgers remain positive? I have to have more pluses than minuses. Here I have to have more forwards than backwards, and I have to have enough of a gain as well. Cool. All right. So the other ones are basically the exact same, is that if I start dead center in the middle, it's basically even money on where the drunkard's going to end. Neither one's going to win in terms of pull. And because the probabilities are both 0.5, I can flip things around. So if I start one click away from the bar, there's a 75% chance I end up at the bar, and then 25% chance that I end up back at home. I'm missing a 1. There should totally be a 1 right here. Second typo I found. I'll fix that and get it posted again. If I start in the bar, obviously I'm going to end up at the bar. So that should be a 1 in that bottom right corner. Cool. All right, so that was my scenario where my probabilities were 0.5s across the board. If I wanted to kind of variablify this and basically introduce the forward kind of stumble as a p, so 0.5, or some other general probability, then my backward stumble is going to be 1 minus p. So if I think about my forward stumble as 0.25, then backwards is 0.75. So in general, p forwards, 1 minus p backwards, and I can very easily build up a very similar matrix P. It's going to have 0.5s replaced with p's, and then the other 0.5s replaced with 1 minus p's, but it's going to look nearly identical. So if I wanted to study this game of what's going to happen in the long run, quickly fix my typo before you call me on it. Well, obviously shoving in p is 0.5, you're going to get the exact same transition. But if I were to change it to, let's say, something like a 0.75, so the bar here has way more pull, you're going to see that the probabilities are going to change a little bit as well. So if I start one click away from the bar, and I have this probability of 0.75, what's going to emerge is that there's a pretty decent shot that you're going to end up at the bar at the end of the day, about a 0.675. Wait, I lied to you. And pause on that. I'm like, why does that seem so wrong? Okay, backtracking on that. So I was like, that should be way higher than that. If you start one away from the bar, there's a 97.5% chance that you're going to end up at the bar. If you start one click away from home, then there's only a 67.5% chance that you're going to end up at the bar. And if you start dead center in the middle, it's about a 0.9 that you're going to end up at the bar. Remembering that this is home and this is bar. So here is, if I start at home, I stay at home. If I start one click away from home, there's a pretty good chance that I'm still going to get pulled into the bar. If I start 2 clicks away from home, there's a really good chance that I'm going to end up at the bar. If I start really far away from home, there's a really, really good chance that I'm going to get pulled into the bar. And if I start at the bar, obviously there's a guarantee that I'm going to stay there. So I'm going to get this nice little 1 in that bottom right corner. So if you create the system easy enough to like have the variables, it's kind of fun to play through these different things. So you can be like, okay, what happens if I change the P into a 0.7 or 0.75 or 0.8 or a 0.9? What's the chance that this drunkard's ever going to get pulled back towards their home? If the bar has this epic pull forwards, there's not really a chance that they can actually get pulled back as well. So there's any number of things that you can play around with on these nice little Markov chains. They're easy enough to build up, kind of sky's the limit. They're a really cute way to kind of study classic gambling questions because you basically identify all of the steps and the moves of a particular game. You construct a big old matrix out of it, and then you run it through the nice little power matrix function that we built up before, and you can really easily extract all of those probabilities as well. So as I alluded to before, you're going to have a variety of them on your kind of activities and homework and things like that. I really like writing some of these problems, and they're just a lot of fun to look at. They're not really that hard to do. You just kind of have to extract the information, build up the little system, as well as convert it into a matrix, and then just launch it through the power matrix object, which we now know, and we made it nice and efficient, and then extract some of the information afterwards. So enjoy, have fun.